Get ready for a massive launch sequence. NASA and Ada Space have finalized the integration for the LOXSAT cryogenic fuel demonstration. This mission is critical for validating technologies needed for long-term orbital propellant storage and transfer. We're talking about testing zero-loss storage systems and high-accuracy propellant gauging in microgravity, all paving the way for future commercial orbital depots. This is how we build the future of space logistics. And the dynamics of the thermosphere. Find out what that light show truly represented. And finally, prepare to hear something truly haunting. NASA has released audio recordings of Saturn, and the eerie wail circulating online is not an actual sound of air, but a translation of intense electromagnetic signals. We dive deep into how scientists converted plasma waves into music, and what this tells us about the physics of planetary magnetospheres. Don't miss this deep dive into the sound of space. NASA and Ada Space have finalized integration for the liquid oxygen flight demonstration, or LOXSAT, marking the final pre-launch testing phase at Rocket Lab's spacecraft production complex in Long Beach, California, as of May 14, 2026. Developed under a NASA tipping point contract, the mission is designed to validate critical technologies for long-term orbital propellant storage and transfer. The integrated payload is slated to launch aboard an Electron rocket from Mahia, New Zealand, with a launch window opening no earlier than July 17, 2026. The primary objective of the LOXSAT mission is to mitigate technical risks associated with handling supercold liquids in space. In microgravity, surface tension causes fluids to cling to tank walls and form chaotic bubbles, making tasks like fuel gauging and propellant transfer highly unpredictable compared to Earth's gravity-driven separation. Over a scheduled 9-month mission in low Earth orbit, LOXSAT will systematically validate 11 distinct cryogenic fluid management technologies. The testing suite concentrates on zero-loss storage systems, high-accuracy propellant gauging, and automated internal tank pressure controls. By maintaining liquid oxygen below -297 degrees Fahrenheit without venting mass, the payload will establish essential performance models for future in-space logistics. This endeavor represents a significant collaboration spanning commercial and civil aerospace entities. Rocket Lab has successfully completed the manufacturing and structural testing of the custom Photon LEO satellite bus, which houses the necessary command, power, and attitude control systems. Propulsion and docking mechanics are being supplied by specialized industrial partners. The data gathered from LOXSAT will form the immediate technological foundation for Ada Space's proposed commercial architecture, cryodock. This future facility is envisioned as an autonomous, multi-user orbital propellant depot capable of storing large volumes of liquid oxygen and liquid methane, the key propellants for modern heavy-lift launch vehicles, with a planned full-scale orbital deployment by 2030. This infrastructure-centric approach fundamentally alters deep space exploration constraints. The ability to refuel spacecraft in orbit allows missions to launch with lighter payloads, topping off tanks in space, rather than carrying all necessary fuel for the entire journey to the Moon or Mars. This strategy aligns directly with NASA's goal to foster a sustainable cislunar economy, shifting the agency's role from primary infrastructure builder to a commercial customer for orbital commodities. NASA astronauts Tom Akers and Joe Tanner have been inducted into the U.S. Astronaut Hall of Fame. The induction ceremony took place at the Kennedy Space Center Visitor Complex. Tom Akers is recognized for his extensive mission history, which includes participation in missions SDS-41, SDS-49, SDS-61, and SDS-79. Joe Tanner's distinguished career includes flights on missions SDS-66, SDS-82, SDS-97, and SDS-115. These recognitions celebrate the significant contributions of these two individuals to the exploration and advancement of spaceflight. An astronaut aboard the International Space Station witnessed a spectacular fiery event while observing West Africa on April 27, 2026, prompting scientific interest regarding the nature of atmospheric phenomena and space debris. While looking for the incoming cargo craft Progress 95, the crew member spotted a bright object streaking through the upper atmosphere directly below. The object exhibited a tail that grew and then split into a shower of smaller pieces, described by the astronaut as a light show. NASA scientists are investigating the source of the sighting. Although Progress 95 docked successfully as scheduled, the event was not attributed to the resupply ship. Possible causes include the reentry and breakup of a launch vehicle, a satellite, other space debris, or even meteoric material burning up in the atmosphere. Determining the exact source is challenging without knowing the camera's precise pointing angle. The phenomenon highlights the dynamic environment of Earth's thermosphere and exosphere, layers where tens of thousands of objects, including satellites and debris, orbit, and where meteoric material enters the atmosphere daily. Large orbital debris, primarily fragmented satellites and launch vehicles, is concentrated within 2,000 kilometers of the surface, moving at speeds of approximately 25,000 kilometers per hour. Orbital mechanics dictate the fate of this debris. Objects below about 600 kilometers typically fall back to Earth within a few years. Debris above 800 kilometers can persist for centuries, while objects above 1,000 kilometers can circle the planet for thousands of years. As debris descends into thicker atmosphere, increased atmospheric drag and compression heat the material to extreme temperatures, causing it to break up and vaporize. The images captured by the Expedition 74 crew, taken on April 27, 2026, provide visual evidence of this event. These photographs, provided by the ISS Crew Earth Observations Facility, are crucial for scientists studying Earth observation and space environment dynamics. NASA has released hours of audio purporting to be the sounds of planets, with recordings from Saturn circulating widely and eliciting a haunting response from the public. However, these sounds are not actual acoustic waves. They are representations of electromagnetic vibrations converted into audible sound by instrument teams. The popular narrative suggests spacecraft record mechanical sounds from planets. In reality, sound requires a medium like air to propagate pressure waves, which is insufficient for interplanetary space. Spacecraft like Voyager and Cassini are equipped with antennas designed to detect oscillating electric and magnetic fields within planetary magnetospheres. The Saturn recordings originate from the radio and plasma wave science instrument aboard the Cassini orbiter. This instrument captured electric field oscillations in the kilohertz range, frequencies outside human hearing, and instrument teams shifted and compressed these signals to render them audible. The specific emissions studied were Saturn kilometric radiation, a coherent radio emission generated near the planet's auroral regions by electrons spiraling along magnetic field lines. The resulting audio features rising whistles and a pulsing low drone. These features correspond to real physical processes. The whistles are characteristic of cyclotron maser emission, while the drone reflects the planet's rotation, with measurements suggesting a complex, variable rotation period. The eerie, musical quality of the audio is not a direct sound of the planet, but a consequence of the translation process. Teams employ methods such as direct playback, sonification, mapping data like brightness to pitch, and heterodening to convert electromagnetic datasets into sound. This translation shapes the perception, as the frequency sweeps and harmonic relationships in the radio emissions happen to resemble pitch contours that the human ear associates with music, creating an evocative, almost intentional structure. Similar sonification techniques have been applied to data from Jupiter, Uranus, and Neptune, producing sounds that resemble bird calls. Meanwhile, Mars rover recordings capture genuine acoustic pressure waves from the thin atmosphere, highlighting the crucial distinction between acoustic data and electromagnetic sonifications. Ultimately, the audio files are not literal sounds, but structured electromagnetic radiation rendered into a sensory format. This process triggers a psychological response of awe by bypassing visual saturation and routing information through hearing, forcing cognitive reorganization. The recordings serve as a case study, demonstrating how the way data is rendered for a terrestrial audience can be as significant as the underlying physics. While the exact rotation period puzzle remains unresolved, the audio captures the complexity of Saturn's magnetosphere, showing that instruments are listening to a different signal, electromagnetic fields, and translating them into a format that engages human perception.